the Taylor series. Let me just put this up there and then I'll kind of get into it a little bit. This is on 201 is where you want to be. All right. Essentially what we're going to be doing is we're going to be looking at a polynomial function, and there's models that I can show you. I didn't put any in this today, that we're going to use functions that we can understand and we could potentially graph and we could create to approximate other functions that are much, much more challenging. And in some cases, maybe can't really visualize, all right? So what's going to happen is we're going to have some polynomial function, okay, and we're going to use it to approximate some other function. The key is they have to contain at least one point that is the same, some x value that we're going to call c. Okay, so there's going to be this common point. So what we're going to say is that at some point p of c is going to equal f of c, meaning that's where their common point is. The polynomial has this point, and at the same point c, that function contains the same point. All right. Now, when we're trying to approximate another function, we have to be able to compare their slopes. And because what we want to do is sort of mimic what the graph is going to look like. So what's important is this idea is that in order to improve our approximation, we want the slopes to get closer and closer and closer together, right? And at certain points, they should have the same slope. And so whatever our function is, and whatever our polynomial is, we want them to have the same slope at any given point. And if they end up having the same slope at all the points, right, then it's the same thing, and we've really improved our approximation. But we want to get it as close as we can without, spending days and days and days doing this, okay? And so that means at that particular point, the slopes would be the same. So the first derivative at c of the polynomial is going to equal the first derivative at c of the function, okay? And so if we do that for the slope, we can just keep going, and we can do that for the second derivative, and we can do it for the third derivative. And as those derivatives get closer and closer and closer, as we look at more and more of those derivatives, our polynomial will get closer and closer and closer to the function, okay? And so we could do this for the second derivative, the third derivative, fourth derivative, and you could just keep going. And that's kind of what the Taylor polynomial is, okay? So that, when we put that together, we get what's called a Taylor polynomial expansion. And so here's what the Taylor polynomial looks like. Okay. Oh, but before, because I was talking about this and somebody immediately, of course, in this Swifty world that we live in, I decided to find a picture of Brooke Taylor, and there he is, in the 1700s, okay? Not Taylor Swift, Brooke Taylor. Although Taylor Swift might be jealous of his hair, I don't know. Seems very curly. He's from England, was from England. But understand how old this is, okay? Just to give a little bit of historical perspective. He was born in 1685, right? Like, this stuff has been around for 300 years, and they still keep using it as a way to come up with approximations. Anyway. Okay. If f of x has derivatives of all orders, meaning it's an infinite polynomial, it can be approximated by this function. Drum roll, please. And here we go. The tapping is not working. Of course, there it is. Okay. This is called an nth degree or nth order Taylor polynomial centered at C. Okay? So let's get into what this actually is. So we always have the first term is just f of c. Okay, then the next term is going to be the first derivative at c times x minus c. Okay, this is the difference between, this essentially is the difference between the point on the function and the point on the polynomial. Okay, because the polynomial that we're coming up with, that's at c, and that's our function. All right, then it's the second derivative over 2 factorial, not a coincidence. Second derivative, 2 factorial. And then this term is squared. So look, second derivative, 2 factorial, squared. Okay, the next term, third derivative, 3 factorial, third power. Okay, and that just keeps going like that. Now, one of the things that I will tell you is after the 3 tick marks, we stop. We don't keep, I mean, you could, but if you wanted to talk about the fourth derivative, we don't put 4 tick marks. We put a little 4 like that, and it would be like that. Okay, and so for every derivative beyond the third derivative, you're just going to write the little number, the power, if you will, in parentheses to indicate fourth derivative, fifth derivative, etc. Okay, and then we end with the general form of it. The nth derivative over n factorial times x minus c to the n. You will practice this a lot. I would tell you you need to memorize it, but you're going to practice it so much you will end up memorizing it. Okay, but needless to say, you need to know the general form of a Taylor polynomial. Okay, now this is the polynomial. We're going to get to Taylor series in a minute. Now, there's another lad who worked on this a little bit. Okay, and his name is, I've heard it pronounced Maclaurin and I've heard it pronounced McLaren. I don't know which one is right. And I actually don't care. I'm going to call it Maclaurin. To me, that's how you would pronounce that word. The difference between a Taylor polynomial and a Maclaurin polynomial is just that it's determining that c is 0. It's when it is centered at 0. So meaning all of this, but the c's are all zeros, which means my x becomes x squared, x to the third, x to the fourth. We don't have to worry about taking the difference anymore. That is what the Maclaurin, oh, there he is, Colin Maclaurin. So he was, I don't know if they were contemporaries, but, he was a little younger than old Brooke Taylor. Anyway, yeah, again, Taylor Swift would probably be jealous of that hair. So this is what the polynomial expansion looks like for a Maclaurin, okay? So again, c is just 0. This is a very common one. It gets used a lot. The only difference, again, is the c's are all gone because the c's are 0. Okay. So these are the general ideas, right? The first term. So the other thing that happens with these is, when we talked about the series before, it sometimes started at 0, sometimes started at 1. The same thing is going to happen here. Okay. Sometimes the first term is going to be the first term. Sometimes the first term is going to be the 0th term. Okay. And so just understand that can happen a little bit as well. All right, let's get into an example just so we can start applying this a little bit and you can kind of see one of those questions, like what is it good for, okay? So this is example 1 on page 201, okay? Did I skip a... No, I did not. All right, so example 1 is saying find a Maclaurin polynomial to the 5th degree, a 5th degree Maclaurin, which means you're going to go 5 derivatives. All right. And we're going to do the polynomial expansion for e to the x. Yes, I understand. We know what e to the x is and what it looks like. The whole point is to practice using a Taylor series or Maclaurin series or a polynomial on something that we kind of know. Okay? And this would be a good example where I could show you that the polynomial that we're going to come up with is an okay approximation for e to the x, but it's not a great one, okay? And maybe I'll pull graphs up for that for tomorrow as well. We start off with literally the easiest function because when we take the derivative of e to the x, we always get the same thing, e to the x. Now, so of course, all these derivatives Okay, or just e to the x. Easy enough. I saw a meme the other day too. It was about the one. Oh no, it's not that one. It was like, I'm going to change you. You know, it's a relationship, and the girl's thinking, I'm going to change him, and it's e to the x, and it's always e. Something like that. Anyway, all right. So if all of these, so since it's a Maclaurin and I'm finding it centered at 0, all right, e to the 0 and all of these is just okay. So in this case, the e to the x is this is a polynomial you're going to need to know, and it's the easiest one out of the ones you need to know. Okay, so I start off with f of x. Okay, so what we're doing is we're coming up with this polynomial, 5th degree polynomial, and so I take f of x, then I take the first derivative, and technically I should divide by 1 factorial, but you know, it's just 1. And then you're going to divide by 2 factorial, and 3 factorial, and on and on and on. Okay, but here's where it gets a little different. Okay, because it's x, it's not e to the x anymore. This is what the 5th degree polynomial of e to the x looks like. Okay, and this is where it like I said, where it seems like a little strange. Like, how could e to the x equal that? Why is there no e to the x in the problem? Well, that's sort of the greatness of these polynomials, is that they aren't going to have that in it. There's going to have, it's just that these polynomials with all the different crazy factorials and all the different derivatives that you're going to have, and since this one's a Maclaurin, so there's no x minus a number squared or x minus a number cubed, it's just x minus 0, which is x. That if we expand this out infinitely, okay, like this is an approximation for e to the x. It's probably not a great one. But if we went out 10 terms or 12 terms or 30 terms, then that polynomial is going to go closer and closer and closer to e to the x. Okay. So this is a good, again, it's a good approximation. If you extend it to an infinite series, it becomes exactly correct instead of an approximation. So if I can take a series of this thing infinitely, it will be e to the x. Which, if you can think, in 1700, somebody figured that out. Obviously, they had nothing but time on their hands, right? What else were they doing? I don't know, right? I can't imagine what life was like in 1700. But imagine just this, sitting in a room with lights. That was not a thing. You know what I'm saying? So, like, strip away everything you know, and you're just sitting alone in a room. Like, what else are you going to do? Think about stuff that's crazy. Like, let's draw a little curve. What is this? Okay? And so, but because of that, we have this. So, yeah, it's pretty cool, in my opinion. All right. What's this? Oh, okay. I couldn't remember what I wrote down, and I couldn't read it. It was very small. So, just in terms of an nth term kind of thing, okay, now here's where, again, it gets a little tricky. This is the 0th term, right? This is x to the n over n factorial, and this goes on and on forever. So this is a 0th term, first term, second term, third term, fourth, or nth term. Okay? This would be an infinite series of the Taylor polynomial. This is the Taylor series for e to the x. Okay? And understand again what this is. This equals this, not an approximation anymore. When you go infinitely, it will equal e to the x. All right, so let's talk about the actual Taylor series, because this is a Taylor series expansion for e to the x. This is a Taylor polynomial to the fifth degree Taylor polynomial. Do you understand the difference?
I thought it was in
Yeah, Maclaurin. Maclaurin is a form of a Taylor. Yes, it is a Maclaurin. You're right. All right. Here are the two forms. Okay. We've really not done much different. All we've done is we've said, hey, it goes on and on forever. That's what makes it a series. It's the same thing as what we looked at on the other page. Okay. It just goes on and on forever. That's what makes them an infinite. That's when we talk about a series instead of just a polynomial. Here's the key thing here. These are power series. You notice we're multiplying by x every time, or x minus c every time. It's not quite a geometric power series, and it's because of the fact that we're not multiplying by the same thing every time because of the factorial. And also the derivative is going to not be geometric. Okay, so don't think that it is geometric. There are some special cases that end up being geometric, but in general they aren't. And I'm going to tell you about the one special case eventually. Not today, though. Okay, today is not that day. Actually, let's just keep going. We got 10 minutes. Let's do another example. Okay. We good to move on from this slide? I feel like this one weird. It shows up blank on my page. Blank. There we go. Okay, example 2. Again, another box with some of the stuff. Here's the difference, okay? We are finding a Taylor polynomial, fourth order, so fourth degree Taylor polynomial, and a Taylor series for f of x equals cosine x, centered at pi. So that's why it's not a Maclaurin. If in order to be a Maclaurin, it has to be centered at 0. All right, and so notice here, and the way that he created this workbook, I think it's nice to have the box. It helps keep you sort of organized. Because in a lot of the problems, you're going to have to find several of the derivatives and then evaluate several of all those derivatives at the whatever it's centered at. Because that ends up being the multiplier over 2 factorial, 3 factorial, 4 factorial, 5 factorial. And then in this case, since we're centered at pi, all my x, I'm going to have x minus pi's, a bunch of x minus pi's. X minus pi to the first, x minus pi to the second, x minus pi to the third. And of course, we're very familiar with the cosine function, okay? But we're going to be able to express it as a polynomial. And again, I'll show you those graphs tomorrow. I'll make sure to have those for you tomorrow. So what I want you to do is start filling that box out. Find all the different derivatives, evaluate those derivatives at pi, and let's see what you end up with. So you can do these different ways. You can find each value and go along and do them as you go, or in this kind of format, I like to just do all the derivatives first and then evaluate them after. It doesn't matter how you choose to do it. So we start off with cosine here. Okay. Differentiate that, negative sign, differentiate this, negative cosine, differentiate that, sine. And we start over again. Okay. When I evaluate at pi, all right, this is going to be what? Negative 1. When I evaluate this at pi, 0. So these ones are going to be 0, right? Those are easy ones. And once I have negative 1, 1, negative 1. Okay. Did you have that? All right. So now let's set it up. Okay. The key thing is, remember, we got the 0th term, the first term, the second term, the third term. And so our factorial goes along with that. Our power on our binomial goes along with that. All right. So here's what your fourth order should look like. Do you want to try setting it up first? Yeah, try setting it up. It's okay. And then when you're done, you can take a look at the screen and see if you got the same thing as me. One of the things that is challenging about writing Taylor polynomials or Maclaurin's is keeping everything in your head straight, okay? Making sure you're following the pattern correctly. And the question of, do I have to write the zeros? I would, okay? Because even though some of these problems eventually are going to say write the first 4 terms, okay? Or find the third order term, something like that, okay? Following the pattern is going to make sure you don't miss something. And if you try to do too much work in your head, you could miss something. There's going to be a lot of terms, and there's going to be a lot of way more sophisticated stuff than this. Like this is the second example you've seen, okay? So I encourage you, even with the zeros, to write them, right? Now, we're going to learn what the expansion is for the cosine anyway. Okay? That's going to be one you're going to have to know. But let's simplify this down a little bit, okay? But again, notice that the second derivative, 2 factorial, second power. Third derivative, 3 factorial, third power, okay?
Teachers, please pardon this interruption. For all students who are helping with the second round of Easter egg today, head to the gym now. Thank you.
Come on, there we go. Okay, so instead of f of x, what we're going to do is we're going to substitute x minus h in 4x. So that's where that, sorry, I said h. X minus pi, okay? And so that's why my polynomial is going to look like that, okay? So it's similar looking, but I just simplified it a little bit, okay?
How would you write the
Good question. I will give that to you tomorrow. I'm going to stop here, though, because I think this is a good place to stop. As promised, I found a little video that kind of illustrates how the more terms you have of a Taylor polynomial, the closer and closer it gets from being an approximation to actually equaling the function. And so this video simulates about 5 or 6 terms of some common functions that we know. And so what it'll do is it'll put the original function up first, then it'll start adding terms to a Taylor polynomial to show how it changes over adding each term. And I think it's a good visualization for what we're kind of getting at. Oh, we have sound. I don't want the sound. There we go. I did not want that. So there's your sine function. And now there's the first couple terms of the Taylor that goes with the sine function, which is one you're gonna need to know eventually. But if you notice, so as they add terms, the curve, the green curve, which is the approximation, gets closer and closer to looking like the actual sine curve, right? So I think they went to the 5 or 6 terms there. Now here for the cosine, this is the one we looked at yesterday. We came up with some of those terms yesterday. Of course, there's your cosine function, and then, you've got some pretty basic looking functions. And as you add more and more terms, you can tell that it's getting closer and closer and closer to looking like that cosine curve. And eventually, like we talked about yesterday, if you add an infinite number of terms, which obviously you can't humanly do, you would have the actual function. Okay. Those 2 functions are pretty good for just, a handful of terms. The e to the x1, you really need a lot more terms, as you'll see here in a minute. As they start adding terms, there's parts of it that seem kind of close, but the left side keeps flipping back and forth, and you really have to expand that polynomial a lot further to get it. But you can even see on the right side, it was getting closer, right? I think this is the last one that I put in this. There's all kinds of videos like this, and there's programs. I think the most frequent place that I've seen it is Desmos, where you can add all the different. Actually, you can do it on your calculator too. If you add in y1, you put the original function. In y2, you put the first term, and then you add. Then in y2, you say y1 plus the next term, and then y3 is y2 plus the next term, and then you can do that visualization on your calculator if you want to prove it to yourself that what I'm telling you is true, which, you can do that if you want. But anyway, hopefully you get the point, okay? And just have a little bit of appreciation for the idea that 300 years ago, this guy, in his free time, I suppose, I can't imagine there was a paying gig, was discovering this, right? And he was graphing these functions out, on, I don't know what parchment or something, you know what I mean? What else would he do? He's carving it into a tree, I don't know. You know what I'm saying? But that's what it was. And so think about the dedication that took, right? And he came up with something amazing. We keep innovating over time, and we keep developing new things. So anyway, all right, I digress. Let's go back to this page. Okay? So here's where we left off yesterday, and I want to show you how to use this fourth degree Taylor polynomial to estimate the cosine of 3. So what we're saying now is, of course we can type the cosine of 3 into our calculator, right? But what we're saying here now is that we're going to say x is 3, because f of x is the cosine. Right now we've said it really should say, I know I wrote that up there yesterday, but it really should say, f. All right, here we go. Perfect situation. Tapping, it's not working. There we go. F of x minus pi is really what we have here. And so what we're going to do here is we're just going to plug 3 in for x. Okay? 3 in for x. So we get something that looks tapping, not working. There we go. Okay, so I just plugged the 3 in for x using the terms that I have. Again, it's an approximation. We aren't using the Taylor polynomial to come up with an exact value. We're using it as an approximation. And later on, we're going to talk about how far away it is from the real answer. And that's called the remainder or the error. We're going to get to that actually couple sections, I'm going to say. Right. So go ahead and plug that in your calculator and see what you get as a decimal. What's tricky here, we talk about three decimal places on the AP exam. With this kind of stuff, I don't advocate for that. I advocate for many, many more decimal places. I think it's almost like 3 is the minimum number of decimal places that they want. I'm going to get clarification on that. But for problems like this, where we're going to be approximating how close something is to the real answer, I'm going to list a bunch of decimal points. I'm not going to tell you specifically which ones you should do or how many you should do, but I'm going to say a bunch, beyond 3. Especially when we get into situations where they're very close. The actual answer in that are very close. Anyway, this is approximately equal to 0.98 99999 25078. And I I think I listed as many digits as my calculator displayed. And I think what's important about this is to realize that what the actual cosine of 3 is. I mean, that's very close. That's a good approximation, right? And we only use 3 terms. I mean, in an ideal situation, or a real situation for that matter, I mean, we're down 1, 2, 3, 4, 5, 6 places. I mean, I get you could round here, but if you truncated, the first 6 digits are the same. So if you're skeptical about if this stuff works, I mean, this is one example, obviously, but I mean, come on, that should be a little bit convincing, right? Let's look at some more examples. Let's go. This is example 4. Okay, so we're going to use the Maclaurin. And now we're going to find sine of x. Okay. And actually, I want you to do this one. What I encourage you to do. Fortunately, we know here as we differentiate sine, we're gonna oscillate between some variation of sine and some variation of cosine, right? So we're gonna have zeros and ones and negative ones in here, but go ahead and fill this out. This is we're going 5th degree here, and then what we're gonna do is we're gonna write the Maclaurin polynomial for the first of the 5th degree. Okay, so like I said, this is what you should have gotten for your table. Okay. Sine, cosine, negative, cosine, sine, cosine. That just repeats, right? Check me, make sure I'm right. Am I right? Is that what you got? Okay. Now I think, let's see if I did. I hope I did. Nope, I didn't. I left the zeros out to save some room. So the first term, which is normally a constant, but that normally is a 1, is not. It's just going to be 0. Okay. My second term is going to be 1x. Then I'm going to have another 0 where I would have the x squared term. Then I have a negative x cubed, but now it's over 3 factorial. Then I would have the 4th term, but that's a 0, and then this is x to the 5th over 5 factorial. And here we go again. There it is. Okay. So that is, now notice it said series, okay? It didn't say polynomial. So because it said series, I added and it goes on forever dots, okay? But this is the general form for a sine function. And on that video that I just showed you, that was on there. This is one, you're going to need to know this one too, okay? So notice the difference between the sine and the cosine, right? The cosine started with 1 and was all the even powers and even factorials. The sine skips the 1 and starts with the variables, and it's all the odd powers and the odd factorials. Okay, so that's important to know, and that's something you're gonna. And for somehow in your head, you got to keep that straight. The odds go with sine, the evens go with cosine, and you're gonna need to know that. And not only will you need to know that, you'll want to know that. It's gonna make it so much easier to do. Normally, it'll tell you like a Maclaurin of the 5th order or a 5th degree Maclaurin. This one didn't actually tell us, but it sort of implied it by saying, I'm going to give you space to write this many. Normally it would tell you, find a 5th degree Maclaurin of sine of x. Yeah, they do need to tell you that. There's not a sort of general rule of thumb how many terms you should find on your own if they don't tell you that. So when in doubt, do a little more than not enough. All right. And then here, let's talk about the nth term, the general term. I'm going to put that in here, okay? So we notice that the signs alternate. There's a couple of different ways that we can write that, but we're going to have a -1 to an n, to an n plus 1, to an n minus 1. Any of those to force the sign to change. That's your kind of key with a series that alternates, a -1 to a power, right? I just want to try to talk you through this one a little bit. This is the first term, right? But underneath here, let's see, how did I write it? The trick is you have to have odd powers, right? Well, let's start with the idea of even powers. I know there's not even powers here, but if I was to have an even power, what would that power be? How could I symbolize a power that would always be even? What would be the best way to do that?
Is it the
2n, right? So if my power is 2n, that will always be an even power, because our n's have to be integers, okay? So if we know that evens are always 2n, what we typically do, you could do it differently, but what we typically do is we just take that even number and we subtract 1 from it. You could add 1 to it, but usually that shifts everything the wrong direction. Right? Long story short, here's how we're going to express our general term. Okay. So -1 to the n minus 1, right? Because our first term is positive. Term 1n is positive. So you could have said n plus 1 instead, because this particular part of the general term just needs to oscillate between positive and negative. Right? That part's not as important. This one is a little more important. I need to make the first term, I need it to be a 1 underneath, because technically it's over 1 factorial. Okay. So I test it. I plug a 1 in, and I go 2 minus 1, that's 1. Okay, good. So if you had a plus 1 here, your powers would be all shifted. It wouldn't work. But with a 1 here, now it's x to the first. The second term, that's 4 minus 1, that's a 3. And the same thing here. So again, like I talked about a little while ago about your quiz, test a few. Make sure that your formula is going to work. Okay? And there's your general term for Maclaurin for sine of x. All right? Come on. There we go. All right, let's look at one more. Okay. So now we're kind of shifting our terminology a little bit. Right? Find a power series for f of x centered at c equals 1 if f of 1 equals 2, and we're finding the nth derivative at 1, and that is n factorial. Okay? So there's a lot going on here, and there's a lot of verbiage, and your first thought might be, what are you even asking? Okay? Remember that a Taylor series is a power series, right? That was something we talked about at the beginning. So in the wording, it's implied that power series means create a Taylor series for this. Okay. Now this one does not tell us how far to go. It doesn't tell us to what degree we need to go. It doesn't tell us how many terms we need to show. But what is important is that because it says it's a series, that means we are going to have an nth term, a general term. So you probably want to come up with a handful of terms until you kind of get the feel of it. And then, so what's a handful, right? To me, a handful is 3 or 4 terms, maybe 5. 5 is probably too many. Okay, I would say at least 3, but to have confidence, probably 4. And then also the general term. Okay. Now, the way this starts is the same way we started those other problems. Okay, we're going to start with all the derivatives. And I'm going to find, I know this is 4 terms, but it's 3 derivatives. So when I'm talking about a handful of terms, to me, the handful of terms is the first term plus the 3 more derivatives. That's kind of my general rule of thumb. Plus, I don't like writing the little parentheses derivatives. I like to give me my 3 tick marks, and then I'm good from there. But it gets too, I don't know. That's just me, I guess. All right. So what we can do is we can figure out all of these things just from what they've given us, right? It looks like this might be a blank sheet. I don't know. What is f of 1? 2. They tell us that, right? Hopefully that's put there. No, I did not. Okay. And then the first derivative is 1 factorial. The second derivative is 2 factorial. The third derivative is 3 factorial. Now, remember what the derivative is. It's almost just like the coefficient that goes with that particular term. Okay, and that coefficient is always over some factorial in a Taylor. Okay. Now, so here's what that's going to look like. So my first term, my second term, this is like the coefficient again. This is like the coefficient. This is like the coefficient. And so what it ends up looking like nice. There we go. Okay. So I got my first term. Then I have my coefficient. It's over 1. Okay. Since it's centered at 1, it's x minus 1, right? On the Maclaurens, it would just be x, or x squared, or x to the third. But because it's centered at 1, I have to subtract that 1. If this was a negative, then obviously this would turn to plus. All right. So then my derivative. Actually, I'm going to highlight that. So these go with these. Like I said, it's kind of like the coefficient. And then you divide by 1 factorial, 2 factorial, 3 factorial, 4 factorial, and on and on and on and on. Right? That's what the Taylor polynomial does. Now, the thing that's interesting is as we go to express this general term or this power series, because right now I haven't expressed it as a power series at all. Meaning I need sigma notation, right? That's what a power series means. Well, hopefully you notice that I have kind of a power series looking thing right here, but then I got this 2, right? Normally this is a 1, and I can't just multiply, I can't multiply the whole thing by 2 because they're not all multiplied by 2. So what you can do is you can kind of isolate it and go, all right, let's just kind of write a power series for that. Okay, and then tack a 2 on. You're allowed to do that. Okay. So what I want you to try to do next, so I'm going to give it away to you that it's going to look like this. And so what I want you to do is try to figure out what goes here. So that was a good question. Can you? Not only can you cancel out, you should cancel out. Right? Doesn't that make writing the nth term really easy? Okay. So that's important. As you come up with a few terms and you realize I can reduce this thing down, this problem gets really easy. X minus 1 plus x minus 1 quantity squared plus x minus 1 cubed plus x minus 1. You see what I'm saying? So yeah, then coming up with that is actually really easy. All right. And I don't have to n minus 1 or n plus 1 or anything like that. Like the first term is the first term. Right? If you wanted to start at n equals 0, you could. Then you'd have to shift your power, right? If I wanted to start at n equals 0, which is fine if you want to, what would change about this? It would be n plus 1. Okay? If they were evens, this would be a 2n. If they were all just odds, 2n minus 1 or 2n plus 1.